Hello, everyone, and welcome to today's webinar hosted by the International Irradiation Association, or the IIA. My name is Thomas Kroc, and I am the U.S. representative of the IIA. I'll be your host today. We're happy to have attendees from around the world and appreciate your time, taking the time to be here. Before we begin, a quick introduction to the IIA. The International Irradiation Association is a not-for-profit organization that supports the global irradiation industry across all technologies, applications, and sectors. We promote the safe and beneficial use of irradiation and serve as a bridge between science and industry, communicating, advocating, and educating on behalf of our members. Membership provides access to publications and resources, working groups, visibility opportunities, valuable networking opportunities, and discounted registration fees for the IIA events such as IMRP 2027, which will be held 12 to 16 April next year, 2027, in Dusseldorf, Germany. To learn more and get involved, visit iiaglobal.com or contact us at info@iiaglobal.com. Today's webinar is titled Practical Implementation of In-House Electron Beam Sterilization, and we're joined by Alex Folz, expert presenter who will be sharing insights on this new opportunity. A few housekeeping notes before we begin. This webinar is being recorded. A link to the recording will be shared with all participants shortly after the webinar is over. You can submit questions at any time using the Q&A function at the top of the screen. We'll have a dedicated session for questions at the end of the presentation. We will endeavor to answer all of your questions, but if we run out of time, we will circulate unanswered questions at a later date. The chat function has been turned off, so please make sure to direct your questions to the Q&A tab. With that, I will stop sharing and hand it over to Alex to give his presentation.
Perfect. Thank you for that great introduction there, Thomas. And yeah, thank you to the IIA for allowing us to present today. All right, and yeah, thank you to all the participants for your time here today. Brief introduction about myself. My name is Alex Folz. I'm an applications engineer out of ATS Life Sciences Systems. So I am located out of the Chicago, Illinois, USA branch. And yeah, I've worked in custom automation for over a decade, experience in both systems design and application. So I've worked on, you name it, for systems, right? Tube sets, auto injectors, diagnostic reagent dispense packaging, and e-beam sterilizers. And looking forward to present our solution today, practical implementation of in-house electron beam sterilization. Our configurable solution to bringing sterilization in-house. So without further ado, I will get straight into the presentation here. Got a pretty good agenda for the team here today. So we'll start just by setting the stage, talking through some classical sterilization methods as well as limitations of those methods. Won't spend too long there knowing the knowledge base of the audience here. After that, we'll jump into talking some of the advantages and differences with electron beam sterilization, as well as a detailed walkthrough of our solution, and hopefully have some time for questions at the end of the presentation here today. So with that, we'll start with classical sterilization methods. Some of the ones I'll run through today include steam, ethylene oxide, gamma, and X-ray. Starting up, we'll talk about steam sterilization. So steam sterilization typically utilizes an autoclave system where the devices to be sterilized are exposed to steam at an elevated temperature and pressure. This moisture lowers the temperature and pressure threshold at which organisms are eliminated, which is the modality of sterilization here. So oftentimes this can be useful and effective for products that can withstand a lot of the heat and moisture of the processes. For example, some of the metallic medical surgical tools you're seeing on the left here can occasionally be a bit more of a challenge for single-use medical devices. Some other advantages of steam sterilization is it's a lower cost sterilization method, and there's a relatively low safety burden. Some some risks inherent to who is directly operating the system, but there isn't any nominal hazardous gases, off-gassing, radiation, so on and so forth. So kind of among the overall modalities of sterilization, it's a relatively low safety burden. Some other methods, ethylene oxide. So the process here with ethylene oxide sterilization is the bulk product is placed into a chamber, air is evacuated and replaced with ethylene oxide. Ethylene oxide is an organic compound, odorless, colorless gas, and yeah, that's really what is being used to sterilize the product. So ethylene oxide can penetrate plastics, it can penetrate cardboards and boxes. So this process is typically done after primary or most of the time even secondary packaging of the device. And alkylation of organisms is the mode of sterilization, right? It's really replacing hydrogen atom with an alkyl group in the organism and rendering it unable to replicate. So some of the benefits and use cases here is the high material compatibility. So at the moment, about 50% of single-use medical devices are sterilized this way. Comes out to about 20 billion. So a significant amount of devices that are sterilized with ethylene oxide. And again, it's very useful for sterilizing products that are heat or moisture sensitive. So those that may be less useful for using steam sterilization. And traditionally with ethylene oxide sterilization, you're looking at bulk sterilization. So an entire pallet of products at a time. Continuing on, we'll move into more of the radiation-based modalities. So the first one I'll talk about here briefly is gamma radiation. So here devices are exposed to radioactive cobalt-60 typically, some other isotopes there, but generally cobalt-60, which generate gamma rays while decaying. So gamma ray photons from that permeate through the devices, including, again, the plastic packaging, sometimes cardboard if secondary packaging is complete, and it typically is delivering 5 to 10 kilogray per hour of radiation to the devices. So given that rate, they're typically, it's a pretty long time for the sterilization process, 30 minutes to an hour, sometimes more. So as part of this process, right, you're typically having all of the cobalt samples in a large racking system, and your product to be sterilized on a complex conveyor system, which will rotate around that cobalt-60 rack. And that's really how you're getting sterilization on all sides of the part. Once the sterilization is complete or you're no longer looking to run the system, that source of the cobalt-60 is lowered into a shielding system, typically a water bath beneath the sterilization area to kind of maintain safety of those while the unit is not in process. So in this case, a little bit less use than ethylene oxide. We're looking at about 30% of disposable medical devices are sterilized this way. Some of the advantages is you get a deep uniform material penetration with the gamma rays that are being emitted. Very good for bulk sterilization, right? Again, having that large case pack of devices rotating around that rack of cobalt-60. And because your radioactivity is coming directly from the cobalt-60, not from a power source, you do have minimal power utilization for processing, right? You really need to power the conveyors that move the product around, the gantry that moves the cobalt-60 around, but other than that, limited power use for gamma radiation. Finally, touching briefly on X-ray. So again, a radiation modality of sterilization. In this case, we are using it's similar to an electron beam system, but we're also using the Bremsstrahlung effect to convert those electrons to a wide spectrum of X-rays, and the X-rays are actually what is directed at the device to be sterilized. Depending upon power here, we're looking at a dose rate about 10x of gamma sterilization, but still not high enough that we're talking, we're still talking minutes, if not an hour for sterilization. We're not really in that seconds or single piece flow region yet. In this case, again, it's a radiation modality, so damage to the DNA structure of the organism is a method of sterilization. Similar to gamma, we're looking at highly uniform dose, deep penetration, again, faster dosing than gamma or ethylene oxide. And one advantage of X-ray is that there's no hazardous materials, no toxins, no toxic off-gassing, no radioactive byproducts, and the safety hazard is removed when the X-ray is turned off. So a little bit of a lower safety burden there with X-ray when the device is turned off. All right, having talked through some of those existing modalities, now we'll talk about some limitations of these methods. Starting off with steam and autoclave. So again, one of the bigger challenges here is limited materials of construction for the device to be sterilized. One of the biggest questions is typically the robustness and the design of the sterile bear to be able to withstand the pressure, temperature, moisture inherent with this method. Working at ATS, working through quoting, automation for a lot of medical devices. I've worked on one or two applications where some of the process parameters for the device weren't necessarily a requirement for the end patient. They were a requirement for the device to be able to withstand steam sterilization, right? So in some cases, you're, impacting your product design to enable the device to be steam sterilized. So certainly a high barrier of entry to allow for steam sterilization there. So again, kind of coming back to the advantages, limited safety impacts make hospital settings a good use case, right? Cleaning off those surgical tools, but again, limited use cases for plastic and single-use medical devices. Ethylene oxide, so it's a known carcinogen among other negative health effects, right? So there's risk in this in both minimal viable emissions as well as any accidental release. And that risk can be both for employees at the sterilization site, even later on in the process stream or in the supply chain, as well as the general population around some of these ethylene oxide sterilization plants. So beyond that, there's also some environmental impacts beyond human health. And especially recently, we've seen many examples of either pending or settled litigation relative to the release, again, both at minimum viable emission as well as accidental release, pending and settled litigation relative to the use of ethylene oxide. So on top of some of that litigation, there's also an ever-shifting policy and regulatory landscape around ethylene oxide. At the moment, some of it appears to be trending to a bit more of a lax regulatory area around ethylene oxide, but that could switch next week, next year, next decade. It's always tough to say exactly where those regulatory mandates will go. In addition to that, there's a lengthy exposure time, so looking at approximately 1 to 6 hours of exposure to the ethylene oxide. And there's also several other phases of the process, including aeration, which can sometimes take days, if not a week, for ethylene oxide sterilization. Finally, there can be some cosmetic impacts to the product. Gamma limitations. So here, as we mentioned earlier, the cobalt-60 radiation source can't be turned on and off like X-ray or electron beam. Really can only be deposited behind the added shielding, the water bath that we talked about. This does lead to both the safety and disposal challenges. So, general safety as well as getting that cobalt-60 out once it's no longer viable. And again, the reason for not being viable is as it's emitting the gamma rays, it is decaying, right? So we've got the half-life of cobalt-60, which is approximately 5 years. We're looking at 12% of that supply lost per year. So eventually, right, you're going to need to get that cobalt-60 out of your facility, bring new stuff in. That also does come with a cost, right? Typical cost here is about $15 per curie. So for a small gamma facility, you're looking potentially in the range of $4.5 million of cobalt-60 per year. In addition, again, you've got a long exposure time to do the sterilization here, so 2.5 to 3 hours. And finally, cobalt-60 is a byproduct of nuclear reactors, so availability of material, kind of both the availability, the supply side and the demand side can be a concern depending upon the volume of reactors coming online as we go into the future here. Finally, X-ray limitations. So again, X-ray being a byproduct of that electron beam via the Bremsstrahlung effect. Going through that, however, we're only getting about 5 to 10% of that initial E-beam power converted to X-ray. So when you look at that 5 to 10%, you're getting a really high burden for power and energy costs, right? So that's one of the reasons that this modality maybe has not seen as much uptake as gamma or other modalities, is just those power requirements to enable an X-ray facility. So that does also lead to some heavier shielding requirements, similar to gamma, looking at requiring more of a bunker, more facilities level shielding and guarding. And again, the exposure time is lower than gamma, lower than ethylene oxide, but it still really limits the process to bulk pack sterilization, right? In your case, in a box, so on and so forth. Finally, we do have some limited facilities dedicated to X-ray sterilization, so not as many as some of the other modalities we've talked about here. Finally, I want to talk about some common limitations of each of these. So I know, having talked through some of the others, right, a lot of those limitations are a little bit more long-term, right? We're looking at where is the regulatory burden 5 to 10 years from now? What does the supply of cobalt-60 look like 3, 5, 10 years from now? What does future safety around ethylene oxide bring, right? What is the power supply cost for X-ray? So knowing that some of that is more long-term, a little bit, some more softer limitations, and we know when you're looking at your choice for manufacturing, you do need to be looking short-term as well, right? What is my ROI? What is the impact next quarter, next year, right? And some of that does come with common limitations of the modalities we talked about, and those are typically the lengthy process times and challenging safety requirements. So when I combine those two aspects together, the majority of medical device sterilization is not done in line and is in fact not even typically done in the same facility, right? A lot of sterilization is outsourced to an ethylene oxide facility, a gamma radiation facility, so on and so forth. But doing this does add a lot of requirements, right? A lot of steps in your process flow, some additional transport steps, right? We obviously need to have work in progress process, so probably more stock at your facility, stock at the sterilizer facility, loading that into a truck, getting that from point A to point B, as well as added packaging considerations and studies, right? In some cases, maybe your final pack out will be used for sterilization, and others, maybe it'll be a temporary pack out, right? But this is all just added expense, added cost, added time, added workflow to your process. And depending upon the efficiency of the process, we're looking at 8 to 9 days in some cases for the device to leave the manufacturing line to when we are having sterilization complete. So having talked through some of those limitations, would like to get into more of the electron beam part of our conversation here today. So why E-beam? Would like to talk about how we can use E-beam to overcome some of our limitations. Is E-beam the solution, right? So similar to some of the other modalities, would like to start with the process and the benefits and the use cases here. So again, start of the process is quite similar to X-ray sterilization. We're using a LINAC, linear accelerator, to accelerate the electrons along a linear beam path. Unlike X-ray, instead of converting that electron beam to X-ray via the Bremsstrahlung effect, where instead those electrons are directly being fired at the product and penetrating the product. So this does yield a higher dosing rate, but lower penetration than X-ray. So, that does, as we'll talk about benefits and talk about much more later in this presentation, gives us the ability to sterilize those products much faster, but just need a little bit more work to do to verify with that lower penetration that we're still getting the sterilization we're working for. Similar to the other radiation modalities, right? Destruction of the organism DNA is the mode of sterilization. And again, once we turn off the system, once we are done sterilizing product, no electrons are emitted after power down, and it becomes operator safe very rapidly after power off. Benefits and use cases here. So again, fast sterilization time. This again is going to be dependent on product size and flow, but again, typically thinking seconds to sterilize a product here due to the high energy nature of the beam. We're getting more of that energy delivered to the parts, so there's no X-ray conversion losses. So we'll get a little bit, more parts sterilized for the same amount of power into the system. It's safe. There's no radioisotopes required, no cobalt-60 here. It is a mature technology based on medical LINACs, often used for cancer treatments, for other therapies. And two big advantages here at the bottom is all of this does potentially allow us to consider processing directly after primary packaging complete or closure of the sterile barrier, and particularly in a case where in-process sterilization is required, right? Something where, I just, based on the needs of the product, I physically can't put it in a box or a pallet or a larger carrier before sterilization. This is really your best option here is E-beam. So, looking at the other side, there is also limitations to E-beam, right? There's usually pros and cons to every modality, and E-beam is no different. So some limitations here that we're looking at is, first and foremost, dose uniformity is going to be very material sensitive. In addition to that, particularly for lower energy and power units, there's limited penetration depth. We're typically limited to processing a single layer of assemblies. Can't really put in its final large carton unless you have a very high energy, very high power e-beam, and the system rate can be dependent upon the product footprint among some other factors. Also on the material side, it has been seen to cause material degradation in some cases. One example of this is Teflon is known to occasionally degrade with exposure to e-beam. If you're more interested in this, Team Nablo has some really good findings on material compatibility testing. They've done a lot of work in this space, but typically on top of, typically what we find is that the best way is just to test it, right? And that's going to be the best way to see how some of your material limitations, if there is any material degradation with the e-beam sterilization. Finally, it is wise to verify process specifications of the product after converting from other sterilization modalities. I think one thing that's important to note on this slide is what you may have noticed here is a lot of the other limitations for other modalities, right, are typically safety, time of sterilization, needing to ship out to another plant, litigation, future regulatory burdens, right? Whereas with e-beam, it's more related to the product, right? So it's more product-based, so some products may see these limitations, others may not. And that gives us a case where, right, we do have the ability to overcome these limitations in a lot of cases. And that what leads me into my next slide here, which is understanding limits. So knowing that most of our limitations are product-based, ATS has developed a very thorough and in-depth process to verify the technical feasibility of a given product prior to entering a quoting phase. So just, kind of don't want to get too into the weeds, but I am showing our, overall process flow map on the left. So some of the needs from the customer, right, is product information. We need a lot of those product drawings and specs, weight, density of the overall product, as well as each of the subcomponents of the assembly, material specifications of each of those components within your assembly, any device requirements and specs, right? So this kind of comes back to the process specs. Do you have a UV adhesive that has a pull force? Is there a leak rate of any of the devices in your system? Is there any, process critical dimensions of the device? And finally, your rate of manufacture and parts per minute, right? So how many of these devices are you looking to make? Ideally, we'd also be looking to get sample product. Sample product is a requirement to go to testing, right? So sample product is really critical for us to go through our process here. And finally, minimum and maximum allowable radiation dose, right? So looking for that minimum level to verify sterilization, and on the maximum side, looking to see if at what level of radiation dose you start to see degradation of the part. That's important for us to know as well. So in a case where you don't know those minimum maximum, ATS is typically targeting delivering a minimum of 25 kilograde of the product with a maximum dose uniformity ratio of 2, right? So that would suggest that in one area of the product, delivering 25 kilogray with a maximum of 50 kilogray in another area of the product. So that kind of talks about what we need from a customer in order to start looking at an e-beam system, but what can you expect out of us, right? So once we get that information from a customer, our steps and commitments are to do both some analytical work, some theoretical calculations, as well as feasibility testing. So really the biggest part of that for us is doing dose mapping. So dose mapping is a process which includes intelligently locating dosimeters under the part and passing several samples under a representative e-beam system. So when we typically repeat this process 3 times, we'll get 3 dose uniformity ratios for each of the 3 times. And from there, based on, how close to 2 we are, if we're up in that 2 range, knowing maybe we want to test a little bit more, a little bit lower, we start to drive a lot of confidence in the product. And out of that testing, we're getting an expected dose uniformity ratio for the product. So this testing is really what drives technical feasibility, right? Is your product a right fit for e-beam sterilization from a technical perspective? That's really our goal there. Kind of in parallel with that feasibility testing, kind of more of that, in the lab style testing. We'll also be taking those results in conjunction with some theoretical calculations to determine the product speed at which we can pass your product under the LINAC. And that's kind of where we start to determine commercial feasibility, right? So putting these two together, we get the technical feasibility. How many parts per minute can I run through the system? That starts to give us commercial feasibility, right? We can know if this can compare that to your overall manufacturing rate and develop commercial feasibility there. And that kind of starts to give us both sides of understanding the limit of your product relative to the market. Some desirable product traits, right? So these are kind of just more high level, a little bit generalized here. But for the system, we are typically looking for small batches or individual products, right? That kind of comes back to that single layer product. Generally, we do want all of the products to be inside the sterile packaging or barrier, right? Packaging does need to be able to maintain a sterile environment inside. This could be a primary package device, flow wrapped, blister packed, bagged, so on and so forth, as well as potentially a sterile barrier could be integral to the product, such as a foil seal. So some general product compatibility, some ideal specs are relatively uniform density, top to bottom, smaller parts, typically yield higher throughputs, and finally minimal dead volume, right? The more dead volume you have, the higher area of the part going underneath the E-beam, which sometimes does lower the system rate. You might notice that under product compatibility, I'm using a lot of relative terms here, right? And that is because the best way to determine product compatibility and really start to get down to actual numbers is to do the dose mapping testing, right? That's really the best way to come back with that, both that technical and commercial feasibility. So that leads me to my next slide here. So you'll see now in the chat, a poll will be coming through, looking to see where everybody here is at in their E-beam journey, right? Are you in early exploration? Are you evaluating a specific product? Are you ready to spec the equipment? Have you done dose mapping wherever you are at in your process? We would love the opportunity to evaluate your product ourselves, right? Again, knowing that a lot of what I talked about on the last slide is, really a rough estimate. There's too many variables to really just look at it from a theoretical perspective and say, your product is feasible, I'm going to get X parts per minute. What we really want to do is complete our more thorough analysis, get your product dose mapped by an ATS SME today, and take a look at our product to understand, can we overcome those limitations? Is E-beam a right fit for you? So yeah, please answer to the poll in the chat if you see that, as well as feel free to scan the QR code, and that will take you to a link where you can input your information, and we can start getting that process to get your product dose map today. So I'll pause here for one moment so you can scan that QR code, but never fear, the QR code will be presented again here at the end of the presentation. Having talked through the E-beam process, now I'd like to talk through the anatomy of the equipment that we are going to be presenting to you today, a brief overview on that. So here is the representative ATS system. So one of the big things that you can see here, right, is this is what we call a self-shielded system, right? So this isn't something where you have to fit your facility for the system. The system comes into your facility, right? So you're not having shielding integral to your facility, huge facilities, modifications, those kind of things. It is a self-shielded system. Some other aspects that you can see from the outside that I'd like to talk about on this slide is loading and unloading. So you can see the potential for an operator load as well as a load robot here. That is one of the more custom pieces of the solution, depending upon what your upstream assembly looks like. We have the ability to flex pick product, load it to the conveyor. Maybe it's coming in trays, we can tray load that product. Maybe it's coming in bulk, you could put a feeder bowl and load it to the sterilizer. You could even have an operator load it to the sterilizer, so a lot of options for loading. Once it makes it to the recirculating conveyor, it enters the shielding area here. I'll talk a little bit more in depth about what's inside of the shielding on the upcoming slides here, but it's going to enter the shielding, pass underneath the Linac head where it gets sterilized, come out the backside over here, and be offloaded at, again, an offload robot, potentially an operator, so on and so forth, depending upon what your downstream processes look like. You'll see it better on following slides, but you can also see part of this shielding is retractable. That's what allows us to get into the Linac as well as the conveyor inside of the unit, perform maintenance in there. And yeah, a lot of that shielding is on the platform here to enable that opening of the system. Opening up the system, that does give you a little bit better view of the system here, looking inside. So here again, you can see loading with this robot, parts transfer through on this recirculating conveyor. It's going to go through a labyrinth that's part of the shielding to ensure we're at a safe radiation level outside of the shielding. So passes through the labyrinth, underneath our linac head over here, where that's actually where the sterilization is being taken place. After the sterilization takes place, go through another labyrinth again for the shielding, come out the backside and offload with the robot on the backside. So you can see here, this is the static guarding that, or the static shielding that is still shown here. I've hidden a lot of the retractable shielding just so you can get a better feel for inside of the machine. But here you get a really good viewpoint as well of the retractable shielding platform, where the other piece of the shielding can open up this way. So it opens this way, left and right, and that's what gives you access to perform maintenance again on the conveyor and the linac itself. So now giving a kind of a high level overview here of the system, we can start to get into talking about some of the subsystems here. So looking at the linac itself, the integrated linac is going to be at an energy level of 3 to 5 MeV with a power level of up to 2 kilowatts depending upon the energy level. We'll talk about this a little bit more in the shielding slides, but both this energy and the power level was intelligently selected to balance kind of getting a good DUR for a single layer of parts, as well as enabling that integrated or self-shielding, right? So there's definitely a balance there between getting enough energy to, get all the way through those parts, but also we don't want to be at a point where we're talking facility level shielding. The beam itself, the profile is variable depending upon your product profile. We're typically looking at about 8 to 12 inches in width. And the dosing rate is, again, it's going to be contingent on selected energy level, power, product, other factors. We're typically looking at 1 to 2 orders of magnitude greater than X-ray. Supporting hardware, so within our model here, as well as in the image below, you can see the linac head, but other supporting hardware for the electron beam is we have the RF generator, modulator rack, chiller, which is going to cool both the RF generator and the linac head. And parts will travel through that sterilization zone. So in this case, we have the linac head residing above the conveyor. Again, a customizable width of the line, pending part geometry. I think one important thing to note is, again, there's one linac coming from the top down. Our system does not have one coming up from the bottom where, again, looking at those, getting with a single layer of parts, good dose uniformity ratios from the one from the top. And we're looking at continuous movement of parts on the conveyor passing underneath that linac. Moving on from the linac, we'll move into the product transport conveyor here. Before I get too deep into the technical details, I did have a colleague of mine which described the conveyor best, I think. So he had described it as if this resonates with you, depending upon if you've been to the style of restaurant, but he described it as an industrial version of a dim sum or rotary sushi conveyor. And I think that was a very apt comparison, right? If you've ever been to that style of restaurant. So really what we've got here is it's a recirculating metallic precision link conveyor. You may have seen one of these in a lot of automation environments. I think the most common utilization of these precision link conveyors is a perfect carousel. We've got a little bit more twists and turns in it, again, needed for safety and shielding. This device is servo-driven for speed and position control, right? So we're getting really uniform passing of products beneath the linac, and it's also metallic to mitigate degradation of components which pass beneath the linac repeatedly, right? We know that this conveyor is going to continue going, and we want to have an optimal life of that. One exciting part about using this style of conveyor is getting conveyor position feedback as well as instantaneous current feedback from the linac. We're actually able to do traceability of products as they pass underneath the linac. So again, this is more optional depending upon your process flow, if this is something that you find would be useful for your device, right? But if you have a QR code, data matrix, barcode, we would be able to scan that, track it around the system, and store with that barcode, right, that specific beam current as well as speed of the conveyor. So I can kind of give you an idea of, dose that's applied to your, it's not exactly measuring dose, right, but it could give you an idea of how much dose was applied to that part as it passes beneath the linac. So, and again, as a part of that, right, the speed of the conveyor is synced with the linac's instantaneous current. And again, really what we're targeting there is ensuring every millimeter of the product is dosed repeatedly as it passes through the system. So as part of this conveyor, we do also have our nests here. Our nests are consisting of an aluminum plate, depending, and I'll talk a little bit more on the nests on the following slide, but in some cases, the product can be embedded directly into pockets in the nests, as I've shown here. Larger products could also be deposited to a bin or a fixture placed upon the nests. So any components of the conveyor that could be degraded by the linac, so for example, greased bearings, these are going to be shielded beneath this dual layer aluminum plate here. And one other requirement of the system is having tight radius turns of the conveyor to minimize our footprint for shielding purposes here. Moving on to some other details about our product transport conveyor. So, and this is more specific to the nest plate design. So really, I think what's exciting about these nest plates that are the recirculating aluminum plates, scallop dual level you can see here, is they really need to accomplish three tasks, right? We want them to have that uniform height between the linac and some of the devices beneath it, again, for some of those shielding parts. We do also need the conveyor to convey around very tight corners, right? So as you can imagine, it's, some intelligent design is needed there, right? If you think of a semi-truck, it can't really turn too tight, but we need each of these links to be able to turn around a tight radius. So we need that to be an aspect of them. And we also really want tight product passing beneath the linac, right? Any empty space on this nest that passes beneath the linac is just unused utilization of it, right? So you can imagine if I had 30% open space, that's 30% underutilized linac, right? So we're looking to get as close to 100% as possible. So we're really, with this design, we're trying to get all three of those aspects into one, right? Common thickness, tight turns, tight product packing. And that's really what we're able to achieve with this dual level overlapping plate design. So again, even as I turn, go beneath the linac, you're always getting two plates to pass beneath it. So that's giving us a consistent level of aluminum between the linac itself and some of the bearings, which you can see the hubs where the bearings would be embedded in here in the link underneath. It also allows us dense packing of the product under the linac, right? You can see how around the scallop here, we're fitting the product even around that radius on the top side as well. So, even as we go through these tight turns, how the product relates to one another, then when they're straight going under the linac, we really get that tight product spacing. And again, with those scallops, we're able to rotate each of these nest links around really tight turns, such that our shielding design doesn't need to become unwieldily large there. One other exciting piece of the nest is they're actually a part of the shielding. So again, once electrons reach this plate, their sterilization job is done, right? They've already passed through the product. They've done what we're looking for them to do. So at this point, the aluminum plates are stopping those residual electrons and they're producing limited X-rays, which are more readily shielded, right? And that's, again, what is protecting these components below in the precision link conveyor, and it's reducing the shielding requirements for the remainder of the equipment, which is really what's making self-shielding viable here. All right, so that touches on some more of the detail aspects of the equipment. So now what I'd like to talk about is, what does this look like in a manufacturing environment? So one option that I'm here to talk about today is in line with your other equipment. So that's what I've shown in this image at left here. So some examples of upstream equipment, right? Assembly equipment, test equipment, process equipment, as well as, in most cases, right, going in line with primary packaging, sealing, blister packing, bagging, flow wrapping, foil sealing, or other forms of packaging. So what I've shown at left here is an example of an ATS integration with two assembly modules, right? So two different assembly modules. Those products are brought together in a buffering conveyor, brought through a flow wrapper, which is the primary packaging use case here, and then finally through an e-beam sterilizer. So, in this case, I think it's a good example too that shows some of the buffer selected between the systems, right? So ATS has significant experience looking at the operation efficiency of modules, sizing buffers between assembly modules, packaging, sterilization, other pieces of the system. So definitely a good use case here of showing kind of a full integration through the e-beam sterilizer. I think one other important note to see on this image here is that depending upon the design of the stereo barrier, one exciting part is that e-beam unit can be inside or outside of the clean room. So in the example here, you can see that we've placed it outside of the clean room. Imagine this wall here is the wall from clean room over here to on the bottom is a docking bay area. So, the system does have a relatively large amount of mass associated with it, right? So we know that based on that, we would prefer it to be outside of the clean room here, but both options are available should you, not be comfortable putting the device outside of the clean room after the sterile barrier is closed here. So kind of in addition to going in line with primary packaging and assembly equipment, it is also possible to integrate this solution as a standalone system, right? So it's certainly not required for this to reside in line. Here you could have, say, for example, again, tray handling of product at the in-feed and out-feed. You can imagine the robots I had shown earlier picking parts from trays, loading parts back into trays. You could provide parts from a feeder bowl. You could have an operator loading parts to the electron beam sterilizer. You could even have tray in feed and out feed going to another conveyor for secondary packaging downstream. A lot of different ways to integrate the style of system into your manufacturing flow here. Okay. Machine configuration and quoting needs. So just talking a little bit more about what do we need from you to go further into that quoting process in order to understand all of the more, again, configurable, mostly standard solution with some more custom aspects. So what we need from you is really to better understand some more of the custom aspects of the system, right? So product, again, the packaging state as arrives at the sterilization equipment. We need to understand connected equipment. Are you looking for that standalone integration with operators? Do you have other equipment upstream, right? What is the configuration of products entering the e-beam sterilizer? Is it fixtured in trays? Are there loose on conveyors, right? ATS has experience integrating all of these cases, right? Tray handlers. We do robotic flex picking for loose on conveyors, right? A whole lot of options there, as well as what is the required configuration of the product leaving the sterilizer, right? And this is typically driven by secondary packaging needs. Does it need to, again, be fixtured? Does the secondary packaging equipment, is that planning to be flex picked? In that case, we'll just load to a flat belt conveyor, leave it uncontrolled there. But what do you really need downstream? Other stuff we need is the footprint restrictions, right? So you want to know the size of the install location, right? Make sure that this machine actually fits in the space that we're looking to install it in. What is the weight bearing capability of the floor? Again, we're looking at up to and around 50,000 pounds of shielding, right? So significant amount of mass there. Need to look at that weight bearing capability of the floor, as well as facility ingress route, right? We need to make sure, do we need to plan for any disassembly of our system? Are you able to open up a door if this is further into a facility? Is it on the outside of the facility? Do I maybe just need to go through a dock door? That's just other important parts to look at. Does the system need to be taken apart or not? More process-wise, right, we're ideally looking for min and maximum allowable dosage, right? In the absence of that, again, we'll target that 25 kilogram minimum with a dose uniformity ratio of 2. Right, happy to look at some of the other process requirements that you have, and collaborate on that with you. Product density, other product process specifications, again, any pull forces, leak tests, just things that could be potentially changed by the sterilization process. We prefer to know that up front. And really an output of all of this, right, is we'll work together to come up with that beam energy and current. Final bit of quoting needs is safety and shielding. So again, understanding that install location, help us better understand local regulations, as well as, I think it would be best to talk to your health and safety team to understand if your specific manufacturing location has any requirements that go above and beyond local regulation for e-beam sterilizers. So just some other important stuff for us to know to go through our quoting process. All right, on my last couple of slides here, going to go into a little bit more in detail on retractable shielding theory. So again, how is this radiation shielding designed and validated? So shielding basics, why is it necessary? Again, to protect personnel from radiation. So primarily the X-rays that come off of that aluminum plate beneath the product, but also the electrons themselves. So shielding comes in the form of thick, dense materials. That's why we were talking the 50,000 pounds here. It's oftentimes lead skinned in a stainless steel. That's what we're looking at here. And in our case, trying to maintain the material throughput, right? To maximize that utilization time of the E-beam, we're looking to have a system that doesn't have any doors open and closing coming into the system. And because of that, we've got that conveyor labyrinth that we've shown on the prior slides to provide additional scattering and protect operators outside of the system. So again, electrons primarily delivered to the product. Some are absorbed when delivering the dose. Others scatter off the product and surroundings, particularly that aluminum plate. Those produce X-rays, and that's the main goal of our shielding, right, is to protect against these X-rays. So ideally, we'd have time and distance to protect us from that. However, I know that most of our customers typically have limited space for their equipment, right? So instead of just utilizing pure distance and time to maintain safety, that's where shielding comes in, right? We're using shielding to minimize the footprint impact of this system to, have a tight footprint in your facility. So shielding verification process, right? So I call this verification, again, with the system being configurable. Our expectation is that a very similar, if not identical, guarding shielding package will work for all cases, but belts and suspenders want to go through this full process and verify that that standard shielding package is compliant to your product. So we're typically going through 3 phases, right? Conceptual shielding, theoretical shielding, and finally physically validated shielding. So phase 1, conceptual shielding, right? We're looking to first define the radiation environment inside and outside the machine. So inside, we're looking at process requirements. So, again, dose mapping, this upfront testing, understanding the beam energy, beam current, dose required to sterilize, and what your part design and what that nesting design looks like. So from all that, we'll start to get a feel for what does that radiation environment inside the shielding look like. We also need to understand what it should look like outside the machine, right? So what is that allowable dose rate at the customer site, right? Do you have any local regulations that differ from typical install sites, right? Or again, does your HSE team have any health and safety team have any requirements that go above and beyond local regulations? So absent any requirements, our typical shield design will target an external radiation of 0.5 microsieverts per hour when measured at expected operator location. So, you can imagine from the previous slides where that human machine interface was, where the operator stands, especially in cases where it's manually loaded. That's when one of the more particular expected operator locations will be. So the outcome of this step, right, is really our modifications to that standard shielding package expected, right? We've got more work to do, but just kind of give that estimate of, are we looking at from a start going with that standard shielding package, or do we need to be considering modifications there? Coming out of that step, we're getting into theoretical shielding verification. So this, again, depending upon results of the previous phase, we're going to be starting with the standard or modified shielding package as we get into simulation here. So simulation, we're doing a Monte Carlo technique, and we're iterating on the shielding design with the expected beam operation prior to build and procurement of all the shielding. So again, the general expectation more often than not is we're going to get good results through this step based on our standard shielding package. But again, belt and suspenders, verifying that's the case. We're going to go through that simulation step for every single machine that we provide. And from the simulation step, we're going to get dose rate out of the sheet, outside of the machine, as well as some more info on the dose rate at the product itself. So kind of taking this to verify some of the dose mapping information we previously gotten. Finally, once we've gone through the theoretical shielding verification, at that point, procurement of the shielding itself, other parts of the machine, and our final step is physically validating the shielding. So for all systems prior to integration, we're going to go through and test the shielding, do an adequacy test to validate the integrity of the design and the construction. On our site, we'll be doing a controlled ramp-up procedure to identify hotspots, if any. If we do find any hotspots, we'll be patching those at our site at ATS in Chicago, and we'll also be doing operational tests to ensure emissions meet customer health and safety requirements at the end. Right, so it's a bit of ideally not an iterative process, right? We're ideally not finding any of those hotspots, but at the end, right, we're coming through this full operational test at full energy, making sure that we've met all emission requirements outside of the equipment. And again, this is a part of every machine prior to install it or delivery to any customer site. All right, well, that's a little bit more on our shielding. So that takes me to more of a summary slide here, getting to the conclusion of our presentation today. So E-beam benefits, right? More energy delivered to part. There's no X-ray conversion losses. Unlike cobalt 60, they're safe, no radioisotopes required, right? Again, when you turn this off, the safety hazard is removed. LINACs are a mature technology, right? Based on medical LINACs here for radiation therapy and other treatments. Again, with the short processing time, this allows us to process directly after primary packaging complete or closure of the sterile barrier. And along with that, this is the best option when in-process sterilization is a requirement. So as I mentioned earlier, flash in that QR code again here. So again, where are you on your E-beam journey? No matter where you're at, we would love the opportunity to have your product looked at by an ATS SME, complete those theoretical calculations, have your product dose mapped, get you back that information to find out technical feasibility of your device, commercial feasibility of your device, really go on that journey with you together. So yeah, if you'd like, please scan that QR code now, enter your information, and I look forward to hearing from you. So with that, yeah, that is the end of my presentation. So yeah, I will turn it over for questions.
Thank you so much, Alex. That was tremendous. I want to make a quick observation, though, before we go to the Q&A. So to now, many attempts to address inline and in-house question have been attempted by accelerator manufacturers. And I know that in a previous life, I was one of those. But there's much more to addressing this type of application than just the accelerator. While accelerator manufacturers know this and attempt to address it, prospective users don't go to accelerator manufacturers when they want to consider this option. They go to system integrators. And so now we've got an experienced system integrator, ATS, who in response to a desire from a customer has designed a system that happens to use irradiation, because the goal is to produce a sterile product, not necessarily to build accelerators. And so it's sort of a subtle point, but I think most of you will appreciate it and recognize that this type of shift is necessary for this to be successful in the market. So we do have some time for some questions. Please use the Q&A. We do have some already listed here. So the first one, so is this a standard size and footprint, or is it completely customized?
So the best way to describe it is configurable, right? That shielding is typically going to be about the same size. So the biggest impact to footprint is going to be the load and offload mechanism, right? What am I looking at for loading? You saw in some of our renderings there, we're looking at a robot to load to the system, right? That's kind of assuming your product comes in a conveyor, either fixtured or flex picking loading to our conveyor. But in some cases, right, we might have a larger load unload device there. So that's going to be the biggest impact to the overall footprint. But as far as that shielding design, the LINAC itself, that configuration of the conveyor, that is all going to be very standard in size and dimensions. So yeah, that is much more standard design to be fit into your facility there.
Okay. What's the maximum height of product that you can handle?
So maximum height of product, that's really going to, again, be defined by the dose mapping. So again, it's all relative to your product materials, right? So I don't want to sit here and put an exact number to it today without having it gone through dose mapping. That's really the key to me, right? Is regardless of if your product is 1 inch tall or 3 inches tall, we'd love to get the details on your product, those drawings, get a sample product and send it out for have it dose mapped, right? And really that's going to what defines that maximum height, right? Is what dose uniformity ratio do we get back? And typically we're in that couple inch range, somewhere around there, but don't want to put an exact number to it because it's so material dependent. That's really more what we'd like to do is have your product dose mapped. We'll let you know the dose uniformity, and that will dictate, can my part be 1 inch tall? Can it be 6 inches tall? So on and so forth. So again, that's just, again, showing the importance of dose mapping.
Okay. Do you give support with the calibration of dosimetry, and do you give training for radiation protection officers?
So we would be working with our partners to do some training for radiation safety officers that we're typically expecting that somebody at your site will get trained up in that, but we'll definitely support your team through that process. But yeah, we would expect that to be somebody on your side, not necessarily an embedded resource from the ATS side at your facility for the long term. But yeah, more than happy to support you through that process.
And then dosimetry, what kind of support do you provide there?
So that would kind of come through again with our acceptance test planning. So this is where it'll be a little bit of a collaboration between yourself and ATS, right? So again, I think to Thomas, your point earlier with us being a custom equipment integrator, a lot of what we do is coming up with test plans, acceptance test plans for equipment. So, whether that is dispense equipment, laser welding equipment, packaging equipment, we're always going to work together throughout the machine integration phase to come up with what does that acceptance test look like? What does, what makes ATS confident? What makes the customer confident that you are going to have a working solution when we deliver it to your floor? So as a part of that dosimetry, that would come up as a part of that generation of what I would call that acceptance test plan. So, what exactly does that testing look at FAT would come through that, and that'd be a collaborative process between us and you to come up with, are we running the machine for 2 hours? Are we, doing, I don't know, 100 cycles of dosimetry at the head with various product states to buy off the equipment? What does that look like? So it'd be a collaborative process through the integration phase.
Okay. Are you considering proposing Monte Carlo software in order to facilitate the dosimetry process during IQ, OQ, and PQ, or is the radiation protection or are you just using it for the radiation protection and shielding design?
That's more so for the radiation and shielding design. It's more so for that. Yeah, we would prefer to do much more of an experimental or real world approach at that acceptance test planning phase. So yeah, that is primarily for just verifying that our shielding design is right, because with how large that shielding is, right, you really have you have one shot to purchase that shielding, right? So you really want to get it right. So does show some information on dosimetry at the part, but it's primarily used for that shielding prior to procurement and finishing that design of the shielding itself. So it's more so in that phase. That is correct.
Okay. The other question here was answered before you got into the shielding section, so I'm going to kind of assume that you've already answered that. So what's the status of your first article?
The status of our, I'm sorry, can you repeat the question? First article?
Yeah, first article.
So yeah, so some of the systems we've integrated, right? Primarily what we have done is custom solutions for e-beam sterilizers. So what we saw from doing more custom solutions is this need in the market for a more standard or configurable device, right? We started to find ourselves reinventing the wheel each time, and we said, why don't we look at more of a configurable solution? All right, so that's really driven us to where we are today, and the solution we've presented today is a more configurable or standard approach, right? So a lot of our integrations have been more custom focused, but now we're moving into this more standardized world that we presented to the concepts and designs for you here today.
Okay. Okay, so you mentioned a max DOR of 2. Person asks, is this an acceptable limit?
That's really going to be defined by, and again, that's very product specific, right? So that's, kind of what we put out there as a wet thumb, but that is going to be very, very product dependent, right? So we really need to see, and even the 25 kilogray, right? That's a little bit industry standard, but again, going to be very product dependent, process dependent. So that's typically where we're setting a line in the sand without any additional information from a customer. But that's where if you have limits or if you have known limits, right, we would love to learn that early on in the quoting phase. Or if you really don't know, we may need to work together to find out what is that actual upper end, right? At what point do you start to see negative effects to your product? At what point does that if you have a UV cure bond or some other aspect of your system, at what point do those start to degrade? So, I think we see it as acceptable, but again, very product dependent. And, while a lot of our feasibility testing is more short form, right, we're putting 3 products through the system, it's definitely something we're open to the conversation on, right? And I think, Thomas, to your point earlier, right, ATS is a very large systems integrator. We have a lot of smart engineers here, right? We have mechanical controls, systems design, a whole lot of groups and teams to support. So, happy to collaborate on that process, right? If you don't know the maximum, happy to collaborate on, say, a proof of principle. What does that look like? How do we determine that maximum allowable dose in your product, right? At what point do you start to see negative effects? So if that's not something today, happy to look at potential collaborations to determine that, right? I think that's a lot of what ATS does, right? Is we're typically ingesting customer process specs or supporting a customer and finding process specs for them. Right at the end of the day, our customers do own our process specs, but we're typically always happy to help them better understand how those impact in a manufacturing environment. So happy to support and collaborate there on a technical analysis.
Okay. Well, thank you. That's all the time we have today. There are a few more questions, so we will capture those and answer them offline and post them with the recording. And that special thank you to the presenter, to Alex, for taking the time to be with us and provide the insights to this system. The recording for this webinar will be circulated shortly, as I mentioned, the Q&A questions. Contact information is shown there. So thank you again for joining us, and we look forward to seeing you again at our next webinar. So thank you all.
Yep. Thank you, Thomas. And yeah, thank you to the IIA. Appreciate it.